tautology is a compound statement. Compound means you have connected to at least two statements. That kind of statement is called a compound statement. So tautology is a statement, compound statement, which is always true. So now for instance, if you say x greater than 5 implies x greater than 1, that is true, no? But that's not a compound statement. That's not a compound statement. Compound statement means it is a connection of you have logically, using logical connectives, you have connected them. And that kind of statement is a logically compound statement. Tautology is a compound statement which is true for any assignments. Do I have? Here I have. A tautology is a compound statement whose truth value is true for all assignments of truth values to it is simple statements. It's good for us to know.
So it's like P or not P, has to do the same thing.
Yeah, P or not P, always true. No? That's the tautology. That is the tautology. I have written here. These are trivial. Q are statements, then P and P implies Q. P and P implies Q. This whole thing implies Q. Is a tautology. So there are two statements. There are then four assignments, no? P true, Q true, P true, Q false, Q true, P false, both are false. For any of them, this is true. Such a thing is called a tautology. Tautology must be a compound statement. It is true for all the segments of P and Q, O, R, whatever. So this is a tautology, you can see that very well. Because if you say this must be true, say let's take P, whether it is P true, P is true or false, this statement must be true. For instance, if P is false, definitely true. If P is true, P and P, if P is true, if P implies Q is true, then Q is true. If Q is true, definitely this is true. If P is false, this is true. Whatever the values you put anywhere, it is true. Can you see that? This is a tautology. This tautology is important in a hospital, for instance, or in a plane. In an airplane, airplanes are driven by computers. No? It's not only one computer, several computers. If one computer malfunctions, other computers work. It is like that. Final thing is for instance, in National Hospital, operation theatres, current always goes no. Then the government electricity There are so many variations. My side, electricity dropouts are very common. I don't know why. In surgery theatre, it cannot be. It works always. So that kind of thing here. So another one is PQRB three statements. Totally. PQRB, so that P implies Q and Q implies R. This whole thing depends on this. P implies Q and R. This is also a total. You can try in your head. P implies Q and P implies R. If I do this, P implies Q and R. I mean, intuitively you feel it, no? First one, for instance, the first one, we know that P implies Q. We know if P is true, then Q must be true. So that's how we need to look at. P implies Q. Since P is true, therefore Q must be true. Without, I'm writing in a proof. Here, second one, for instance, if this one is true, that means if P is true, it implies both Q and R. If it is true, it implies both Q and R. So if P implies Q and R, if this side is true, if you assume P, then both Q and R are true. Here also the same thing. If you want, just take a couple of minutes when you go home and you can write it.
Is there a simplest form? Is there a simplest form for number of statements you have? I mean, if we have simplest form.
Simplest?
Yeah, I mean, if we have one statement, we can say P or not P is a tautology. If we have two statements, that one works, and the three statements, that one works. I mean, can there be a simplest form? I mean,
for a tautology?
Yeah, I mean, for three statements, that is true, and
there are many more tautologies with three variables.
yeah, I mean, there's a simplest form. I mean, not so much quantified.
You are asking me, I'm not clear, for the tautology, this kind of, do you understand what he is asking? Simplest?
Kind of. He's asking if any tautology can be shown as like with minimum number of statements, like P or not P, like that.
Yeah, I mean, for three statements, that one works. That is a tautology, the last one.
Yeah. There are some more.
Yeah, some more. And is there a simplest form? I mean, no.
For a tautology?
Yeah.
No, nothing like that. I mean, say for instance, using P, Q and R, you can write many other tautologies. That is a compound statement, that's all. So, I mean, given a statement, if you write the same statement in a different form, in a way, I mean, for instance, this one, this is the simplest form of that left-hand side. But we are not thinking that way here. We are saying compound statements in three variables, which is true always. That's all. Like you said, P and not P or not P. It is the simplest form of the tautology.
Yeah,
P or not
it is for one statement. only.
Yeah, for others also, suppose you write a statement with using P implies Q for instance, then you P implies Q, O, P and not Q, is a tautology. Always true.
Yes, sir. I mean, that one is kind of simpler than that one.
I mean, what do you mean by simpler?
And
As far as the tautology is concerned, all we need to know is, I mean, this book may be having many tautologies to prove that they are tautologies. Here I have, you don't have the book, no? I mean, here one tautology is P implies, within parenthesis, Q implies R. The whole thing implies P and Q implies R. That is a tautology. Tautology has more than one variable for sure. Because P or not P, I think. It's always true. So that's all. Simpler form, nothing like that. As far as a tautology is concerned, you need to check whether there are at least two variables, whether it is always true. That's all. You don't need to worry about whether it is written in the simplest form or whatever. I mean, if you can, now, for instance, first one is a tautology, you must be able to say, when you say P implies Q, you don't know whether P is true, you don't know whether Q is true, you know only P implies Q is true. I mean, if P is true, then Q must be true, that's all you know. But here, P implies Q is true and P is true. Therefore, Q must be true. That you know, I mean, that's what it says. Here, second one, the same way. So, many total P and Q implies P. That's a conditional statement, but I say here, tautological conditional. P and Q implies P, obvious. P is true. For P and Q to be true, P must be true. Then P and Q implies P is a tautology. Tautologies are important for electric circuits, you know, this sort of things.
So all the tautologies are logically equivalent, no?
In a way, but sometimes if you have, here you have PQ variables, somewhere you have RS variables, I mean, no connection, no?
Yeah.
No connection. That's why you need to read, when you find time, ordinary language, logic and daily life. Did you read it?
I read up to 30 pages.
Read it. It's interesting. If you think logic is the thing in the world, this one says no. It's a very good thing for you to do. Just read it. It's very easy to read. For instance, somebody says, Podiya Puhami died at home. I say, consider the statement. Let's not go, because I want to have a plan to visit, cover everything we have done by next Friday. So we should do this. Then contradiction is a statement always false. Against a compound statement. Now, for instance, 2 is odd. That's a false statement, no, but that's not a contradiction. Contradiction is a compound statement which is always false. Tautology is a compound statement which is always true. For any assignments you make for P and Q, first one is true. Any assignments you set for B, Q and R, second one is true. Contradiction is the opposite of this sort of compound statement which is always false. It is like P and not P. Actually, it boils down to P and not P. Any other statement also boils down. Then page conditional proof. You understand the conditional proof, no? conditional proof. See, suppose you want to prove some statement of the form P implies Q. Maybe it is if n greater than 1 and n is prime, then something like that. So conditional proof is you assume P is true. You assume P is true. Then by doing some work, you prove that Q is true. You assume P is true, then by doing so, some rag B or whatever, doing some work, you prove that Q is true. This proves the statement. P implies Q is true. This is called conditional proof. That's why you have, there is a bunch of things. N is even and n greater than 4 implies something. Then you assume that side is true, then you do the many other things and you eventually prove Q is true. You never think about other situations where P is false. Because if P is false, P implies Q is true for sure. So this is called the conditional proof. This in maths, it is a very powerful one because we are proving a little and claiming much more. We false case included now in an example only you will see conditional proof. When you are given an implication, this is one way of proving. Other one is proof by contraposition. P implies Q is logically equivalent to not Q implies not P. So you can prove this statement again by conditional proof. Assume not Q is true, do this and that and so on, eventually you prove not P. Then you claim, actually all you have done was, when Q is false, P is false too. But you are claiming this whole statement is true. So it's a very powerful thing. So anyway, conditional statement or the implication, this is a way of proving proof by conditional proof. This one is proof by contraposition. Another one is proof by contradiction. I want to go to the restroom again. It's raining outside. I'm not sweating because then you don't sweat, you want to go to toilet there.
Might be lazy.
Eh?
Might be lazy.
Could be. Anyway, so there are three ways of proving a conditional statement. As conditional proof, proof by contradiction. Contraposition. Next one is proof by contradiction. You assume P and not Q. Then you get a contradiction. You get a contradiction means you get something you know to be true is you know to be false. True is here. Then true and false, it is a contradiction. So there are three ways of proving this thing that is very important. Very important to know. So, let's see. So many things to do by next Friday. I don't know how much I will be able to do. But let's try. Anyway, conditional proof, you understand or you assume P is true? Prove Q is true. Actually, what you are proving is if P is true, then Q is true. That's all you are proving. But you are saying, no, P implies Q is true. That's the powerful part. Proved by contradiction. One other method. Proved by contradiction is the other method. Then, proved by contradiction is so powerful. This is a proof that your grandmother or grandpa, they don't agree with the proof by contradiction. Why? Because you are given a statement to prove. You assume it is false. Then you write in some bunch of some other, they will say crap. By writing many things, you come to something, you say that is true. Then you claim that the first statement is true. Your grandma will ask, suppose you want to prove P. You assume P is false. You do some other, this and that. You go to New York, downtown Florida, Morocco station. You come to something, statement that we know is true, you are knowing it is false. Then you have a contradiction. Then you say that your original assumption is wrong, therefore P is true. But your grandma will say, hey, you haven't proved P. You see what I'm saying? You assume P is false, and this and that, and now you are claiming P is true. She will argue with you, no, you haven't proved it. You see what I'm saying? So, proof by contradiction is a method among mathematicians. Let's see. Let us use this thing to prove two things, because proof by contradiction is very important. I have to go to restaurant for this. 1 over factorial n going 0 to infinity. You know this is called E. Prove that E is irrational. I will do it, I will go to the restroom and come and prove it. This number is, because e to the x is x to the n over factorial n going 0 to infinity. No? When you put x is equal to 1, you get this. Let's prove this thing. Then you will see the strength of proof by contradiction, however, to which grandmother will never agree. Will never agree. Another thing is, though grandma doesn't agree, that's the only way to prove it also. How can you prove something is irrational? Only thing you can prove is it is not rational. So I will be back and prove it. And some other two examples. After I prove this thing, I want you to prove this one. This number, let's say x is equal to 0.1, 0, 1, 0, 0, 1, 3 zeros and 1, and so on, is irrational. This number is irrational after we prove this thing. Can you see? Because that one I have told you that is irrational, but no proof. After proving this thing, we must be able to prove that I would like you to do it. You can do it. So this thing. Mathematics, no? Okay. So you know what it is now. I want to use the whole board. Again, assume, prove that V is irrational. Prove that. Oh, I have written it. Prove. Suppose E rational. So we are going to follow the proof by contradiction method here. That's the only way, because I mean, there is, how can we say something is irrational? All we know is a number is irrational because it is not rational. That's the thing. Suppose E is rational, thus there exists PQ belongs to, in your way is a plus, such that E is equal to P over Q. Now we need to get a contradiction for that. Because all we know is E is E is 1 plus 1 over factorial 1 plus 1 over factorial 2 plus 1 over 3 factorial plus 2 factorial plus 1 over factorial q plus 1 over factorial q1 plus, like that it goes forward. By the way, even though I'm going to do this thing, you haven't done series yet, I'm going to assume that you know, I mean, we haven't proved this series convergence of the series. We haven't proved it. But if you want, we can prove. But I'm going to assume if R mod R less than 1, then 1 plus R squared R plus R squared plus R cubed, bingo, is equal to R over 1 minus R. You know this one, no? R is a number smaller than 1, absolute value. Then if you add R plus R squared plus R cubed, then you get R over 1 minus R. You can prove this easily. So now we have in break. Cannot remember Q plus 1. So what I do is I multiply Q plus 1 factorial times E. This is Q plus 1 times P over factorial times P over Q. This is equal to Q plus 1 factorial times that thing. In a sense, you know, this proof by contradiction is an amazing thing. We don't prove what we want, but to the contrary, we are assuming if we assume that what we want to prove is false, we are ending up with some nonsense. Contradiction means that, no? Then we are claiming that original thing is correct. That is why proof by contradiction is a proof for mathematicians only. Now, if you want to prove that there are in fact infinitely many even integers, you can give a proof to grandma. Hey grandma, 2, 4, 6, 8. All the way it goes. Puta, I agree, grandma will say. But if you want to prove infinitely many primes, I cannot write 15 primes. You cannot write. But you can prove that if you assume that there are number of primes is finite, you get a contradiction. So as a result, we say that there are infinitely many primes. So you need to remember proof by now. If you want to prove, for instance, even there are infinitely many odd integers, you say 3, 5, 7, 9, 11, etc. You can go as much as somebody wants. But there are infinitely many primes, you cannot do so. Actually, today it is a big challenge to find, if you are good at the computer, you can make some dollars. If you find some new very big primes, you are paid, I cannot remember how much it is worth to try. You know that, no?
Yeah, there's some amount of money, I can't, million or something.
Oh, something. In American dollars. If you find a prime number and get $1 million, take me to Pizza Hut. Because I gave you the room.
Which
Sure.
is the next prime number.
Yeah, after that, there's a prime number that we
Mm.
found, we need a bigger one than that.
I think the last prime was like a book law. It was they written a book for the last prime. I remember.
I'm sorry, I couldn't understand what you said.
There is a book for the last prime number.
They found.
So all
That
the
they have
Yeah.
computed.
all the numbers is in the
All the digits.
all the digits are in the book.
Yeah, number theory is by the way an amazing thing. It is amazing. This guy is a real big shot in tells how he has shaken the world of numbers. Yeah, he is an amazing guy. But first chapter is okay, so we can simplify this thing from where to where. Great. Cannot remember, I haven't seen it recently. You go up to Q plus 1. We can write this one as Q plus 1. Let me write it here. Q plus 1 factorial times n going 0 up to Q plus 1. 1 over factorial n plus n going Q plus 2 factorial. Oh, sorry. Q plus 2 to infinity. 1 over factorial n. Broke into 2 parts. I think I did the right thing. Now, this number, let me write this way, Q plus 1 factorial times, because you need to learn this thing very well to do that problem. N going 0 to Q plus 1, 1 over factorial n, plus then Q plus 1 factorial times n going Q plus 2 to infinity, 1 over factorial n. Now, okay. Now let us look at this last part. Q plus 1 factorial times n is equal to Q plus 2 to infinity. This one you 1 over factorial n. This is like Q plus 1 factorial times 1 over factorial Q plus 2 factorial, 1 over Q plus 3 factorial, plus 1 over Q plus 4 factorial. Like this. Right. Now this is like q plus 1 factorial. You can say this is 1 over q plus 2. Then you q plus 1 factorial times q plus 2 without this. One over q plus 2 you get, no? Right? Then next one you get 1 over q plus 2 times q plus 3. Next one you get 1 over q plus 2, q plus 3, q plus 4. Right? So this is, I can say, strictly less than 1 over q plus 2. So this is strictly less than 1 over q plus 2 whole thing square. Because 2 is smaller than 3. And this here is 1 over q plus 2 cube. Like this. Now, q plus 2 is at least 3, no? So this is like 1 over 3, 1 over 3 squared, 1 over 3 cube. The geometric series. So you get first term is 1 over q plus 2 divided by 1 minus 1 over q plus 2. So q plus 2, q plus 3 cancel out. You get 1 over q plus 1. Right? Because q plus 2 minus 1 is q plus 1. Now this guy is smaller than 1. Right? Is smaller than 1. Now what do I have? I have, therefore, 0 is strictly less than q plus 1 times q plus 1 factorial times p over q minus this part q plus 1, sorry, minus q plus 1 factorial times n going 0 up to q plus 1 times 1 over 2 is it. This is strictly less than. So what I did was, I thought this one is less than 1. Then this guy minus this sum is equal to this one. No? So it is less than 1. Can you see that? Now, q plus 1 factorial times p over q is an integer. Here, all the denominators are at the most q plus 1 factorial. Therefore, this is also, first term is 1. 1 over 1, it is an integer. Q plus 1 times first term is an integer, second term is also an integer. Because you are going from n going 0 to q plus 1, no, n is smaller than or equal to q plus 1. So, therefore, this is an integer. This is definitely an integer. So, integer minus integer is an integer. So, now what do I say? There is an integer between 0 and 1, which is a contradiction. Therefore, p over q is irrational. This idea is used in very many places. this idea. Anyway, now we have proved that E is an irrational. E, although we don't know anybody who can write E, all we know is nobody can write E, I guess. I don't know. Sometimes this is a thing that I wonder. To you also I am saying. Now, over there pattern is 0.1, 0.01, like that, no? Sometimes there may be, say, 10 digits block of blocks. For instance, what I am trying to say is, point now over there 0.1, 0.01, 0.001. So that way, here we can have, for instance, 0.1, 2, 3, 4. Again 0.1, 2, 3, 4. Not point 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Like that. I don't know whether somebody will, before we die, will come up with that kind of blocks. Very large. It can happen. If so, although he is irrational, one can write the nth decimal place. That I guess I don't know, nobody knows. For the time being, no one knows other than this proof anything about E. We can prove that E is less than 3. Did I prove it? No, next. After we began series from the book, let's do it. It's easy to prove E is less than 3. And definitely it is greater than 0. So E is an irrational number between 0 and 3.
Sir,
Yes.
is there a way to write this as something like we write 0.3333 goes and we write that as 0.3 bar, right?
0.3 bar?
Yeah, 0.
No. Then it is
No,
rational.
sorry, not bar. There's a dot on the 3.
No, then it's
Then it is rational.
Yeah, I mean, is there a way to write?
If you can write that way, then E will be rational. No?
I mean, is there another way? Not dot, but something, no?
But other than that, I don't know. I don't imagine. I cannot imagine.
we can write it as 10 to the power minus 1 plus 10 to the power minus 3 plus 10 to the power minus 6, like that.
Prove that it is rational, I mean, you can do it. It's a good exercise. It is a good exercise. If you do that, I understand that you, even though you don't write that well, you think very well. You have to think properly to show that that guy is irrational. Same idea like in this group. Like now I gave you tautology, you know that now, no? Tautology, contradiction. Now example and counterexample. These two words are also important. Analysis words. Analysis words. Example. We in maths, when you say, of course, example has another meaning. We know, I mean, we have many examples, no? But here maths, when you say, so there is an integer n. There it is n belongs to say plus, for instance, such that n squared plus n plus 1 squared is equal to n plus 2 squared. If you give a value of n, that is an example of a value of n which proves this statement. So, for instance, if you got 3 belongs to z plus, and 3 squared plus 3 plus 1 squared is equal to 3 plus 2 squared, am I right? 3 squared plus 4 squared is 3 squared. So, n3 is an example. This is an example of a value which proves the statement there exists. Should not do it. There exists. So, example is a value which proves an existential statement. That's the meaning of an example in maths. The counterexample. Then counterexample. Count. Counterexample is a value which disproves a universal statement. Right? Can you give me a counterexample?
Or
Whatever. It's up to you to give me a universal statement and which
That's
contradicts.
x squared plus 8 plus 41.
I can't do the same problem.
So do you want a statement?
Yeah, because whenever you are giving a counterexample, first you have to give a universal statement. It appears to be true, but you are giving an example
Which is not
which makes it false. Can you give me one? Very easy, but I am just asking from you.
For each n belongs to R, n squared plus 1 greater than 2.
Yeah, you are saying for each.
N belongs to R, x belongs to R,
X belongs to R.
x squared plus 1 greater than 2, strictly greater than 2.
Let's say x square for each x belongs to R. X square greater than or equal to x.
Yeah.
So somebody may think this is true. Then you get 1/2 1/2 belongs to R and 1/2 square, which is equal to 1/4, is strictly less than 1/2. So 1/2 is a counterexample which disproves this universal statement. Examples prove existential statements. Counterexample disproves universal statement. So now I am going to assume I told you these two words also because I am covering up logic now because I really did not teach logic to you, but to the contrary you learn from me. So you want me to write it? No. Count examples prove the existential statements. Count examples disprove the universal statements. The count example is a value which disproves the universal statement. Example is a value which proves an existential statement. That's very important for you to know. Okay, what else do I say here? Theorem. I said, what is this? 96, 15, let's see. They are important because we don't have time to prove and disprove everything. What do I say? 15.2, 14, 4.4. If whenever you find time, read the whole book carefully because it covers roughly whatever needed to do analysis. I don't know whether it covers the logic, I don't know because I haven't studied logic. I know only mathematics. This one, let me say 15.2. You may have read or you may haven't read, I don't know. Okay, so generalized distributive laws, something we discussed early in the morning. Distributive laws, there is a thing called generalized. Generalized distributive laws. Since you have the book, I am not going to write them. Generalized distributive laws. In the morning, you P and Q R, you said P and Q, O, P and R, like that you discuss. No? Here what it says is P is a statement. P is independent of X. Is independent. Independent of X. And Q is dependent on X. So this one statement P and there I use this symbol, there this X belongs to A, such that Px P and there is X belongs to A such that Px is logically equivalent to where it is X belongs to A, such that P and Qx, when P has nothing to do with X, you can take it inside. No? You need to know that you can read the root. No? Again, PO. For X belongs to AQX. This is not that much needed when you are doing maths because it automatically comes to you. That's why it is not needed. It's logically equivalent to. But for each X belongs to A, P and Qx. P and O, P, O. That O, here is O. Qx. I mean, this, we just should go through the proof without writing the word. P says P is like, say, P may be a statement like N is odd, it has no X, Qx is X squared plus 1 greater than or equal to 0. So P has nothing to do with X. If you see such a statement P and there exists X belongs to A such that Qx is logically equivalent to there exists X belongs to A such that P and Qx. I mean, proof is, we don't need to write at all, but you can see, if you assume P and there exists X belongs to A such that Qx is true, then P is true certainly, and there is at least one X0 such that Qx0 is true. So you can say that X0 belongs to A other side, P is true, Qx0 is true, therefore that side is true. Similarly, you can come back, if you assume the right hand side is true, there exists X belongs to A such that P and Qx, that means there is one X0 belongs to A such that P and Qx0 is true. Therefore, P0 is true, Qx0 is also true. Since Qx0 is true, you can say there exists X belongs to A such that Qx. P is certainly true. That is the proof. So, but when you are doing maths analysis, I mean, you don't have to assume this is generalized distributive laws, nothing like that. It comes to you naturally. Second one also the same way. PO for each X belongs to A Qx is logically equivalent to for X belongs to A PO Qx. However, if P has X, you cannot take it in, and then there is no meaning also, because what is inside the square brackets is not, I mean, X is not there. You can say there is T belongs to X such that Qt. No X. If you assume the second one, P over X belongs to A Qx, so if P is true, the right hand side over X belongs to A P of Qx is P is true, P of Qx is true, but whether Qx is true or false. So if this side is true, that side is true, trivial. Similarly, I mean, I just mentioned this because in the book I have written it because students, they don't know, I mean, in A level you don't do any logic, no? But even for O level, I think not that you give a logic lesson, but question should be written logically, that's what I think. Now we say we prove two triangles are congruent. We never prove two triangles are not congruent. So it gives the impression that triangles are congruent. So we have to prove it. Like E is irrational, we proved it. Similarly, triangles are congruent, we proved. No, so it gives the impression that there are no non-congruent triangles. It is not a good thing. I asked when I had workshops at NIE Maharagama for the teachers, O level, A level, they are roughly A level, I guess. Anyway, I asked them how to prove two triangles are congruent, they don't know. So that's not good. It's not a good thing, teachers should know. Now, one way of proving two triangles are congruent is showing that lengths are equal. No? So, if you use that axiom, that thing as the definition, how do you prove two triangles are not congruent? Can you say?
At least one of the side is not equal to this.
No, it has no meaning. Two triangles are said to be congruent if the lengths of the three sides of ABC triangle is equal to the O is OR. No, let's not think about English too much. Equal to the lengths of the edges of the PQR triangle. And if you want to disprove that two triangles are congruent, that means if you want to prove that two triangles are not congruent, what should we do? If you want to prove, we prove both the triangles have same edges in length. No? If you want to disprove, what are you going to do?
At least one of the edges is not equal.
No. It doesn't have a meaning. Your statement is true for congruent triangles also. What you said is true for congruent triangles even.
Two of the edges has to no. At least one of the edges has to be same, and at least one of the edges has to be not the same.
I'm sorry, I couldn't get it.
At least one of the edges has to be the same length, and at least one of the edges has to be not the same length.
Side.
Yeah.
Side.
Sides, edges.
Still, I don't get it. Triangles have three sides. We are not talking about angles here. We are talking about edges. De Morgan's law shows not P or Q is logically equivalent to not P and not Q. Not P and Q was logically equivalent to not P or not Q. So similarly, for every x belongs to a qx, if you take the negation of for every x belongs to capital A, px, what is it?
For every x.
Not for each x belongs to a qx is logically equivalent to
There exists x in A such that not qx.
very good, very good. X you are in. ඒ වගේම there exists x belongs to a qx as a negation.
For all x in A, not q.
Okay, very good. So I'm going to list of logic book over there. I would like there are some natural generalizations, this and that. Although I wrote here, I'm interested in the ones which are used in analysis. Because I am not trying to make you an expert in logic. Let's see. Field analysis. I wrote 3 books now. silly. Proofs, but I don't know whether they are. Let me go through quickly, because then we can start. What I will do is next day or even today, if time permits, I would like to go to the bound, meaning of bounded, unbounded, limit, not limit, lim should be. I want to cover all that. And somehow his definition of lim sup was little difficult at the beginning, but now you are with it. Still it is somewhat artificial, no? The way you take the sequence, you start from somewhere, get the whole set to the end and take the soup of that, inf of that. And somebody can wonder why on earth we are doing this, no? When you say so. So I have a different way of doing it. So here, let me go through. If it comes to something that I should write on the board, then only I will go to the board, otherwise I will just do. Proof of a disjunctive statement. Disjunctive statement is what kind of statement? Can you remember?
O.
Very good. P O Q. How do we prove it? Here I said how to prove a disjunctive statement, how to disprove a disjunctive statement. Both are very important. How do we prove P O Q?
At least one of the POQ.
You prove at least one of them. How to disprove P O Q?
Prove that Q, the P and Q are
Both P and Q are false. Proof of a conjunctive statement. Conjunctive statement is P and Q. How do you prove P and Q?
you have to show that P and Q both are true.
True. How do you disprove P and Q?
At least one of them have to be
At least one of them. Proof of a conditional statement. I have here proof of a conditional statement, conditional proof, proof by contraposition. How to disprove a conditional statement, 3-4 topics. How do you prove P implies Q? There are 2 ways, no 3 ways. What are they? You want to prove P implies Q.
assume that P is true and
Do that.
Q is true. And
One method. That is called conditional proof.
And then the contrapositive proof is that we assume that not Q is true and prove that not P.
Okay, that is called contraposition. What is the other method?
Proof by contradiction.
What is it?
We assume that P is not true. Q.
How do you prove P implies Q? By the method of proof by contradiction.
Q, we assume that Q is not true and something and we have to show that by P and something we know that Q is
No. When you are given P implies Q, 3 ways to prove. One is you said you assume P is true, then you prove Q is true by doing some work, whatever. That's called conditional proof. Other one is P P implies Q is logically equivalent to which contrapositive not Q implies not P. So over there you assume not Q is true, that means Q is false, and prove that not P is also true, that means P is also false. Then there is another method to prove any statement in this world called prove by contradiction. How do we prove it?
We assume the negation of the implication and prove there is a contradiction.
I'm sorry.
Negation of the implication and
So what is it in me? I'm asking.
we assuming P is true and Q is not true, and by that we do some work and prove there is a contradiction at the end.
Assume that P is true and Q is false. No P and not Q is negation of P implies Q is P and not Q. Assume that P and not Q is true, get a contradiction. No? That is it. It's got a proof of how do you disprove a conditional statement?
We have to prove the negation.
We have to prove the negation. Very good. Proof of a biconditional statement, you prove either both are correct or both are wrong. How do you disprove? You have to prove one is true and the other is false. Anyway, proof of a universal statement. How do we prove? For each x belongs to capital X, Px. How do you prove that? For each simple x belongs to capital X, comma, P of x. How do you prove that?
Depends on the condition. Depends on the statement.
No.
We assume that for arbitrary x, this is true and prove that.
You are not telling precisely. That's the thing. Not good. Sometimes Sinhala people in this country, when they go to USA, they have very hard time. You know why? Because they begin to say, you assume this is true. Last part is very last part. The reader, listener can understand. So what do you say? I want to prove, I am asking you how to prove for each x belongs to, simple x belongs to capital X, simple P of simple x. How do we prove that? Say a direct proof. How do we prove it?
Assume that x belongs to x is arbitrary.
Okay.
Then it depends on the statement. It depends on the statement, right? We have suppose
No,
there
my
is.
statement is Px, P of x.
Then you have to prove that Px is true by doing something.
No, your initial words are not good. You said assume that x belongs to x, not that. You can say assume that. Somehow you take some if.
Let x belongs to
Oh,
x.
yeah, because the given set is, if you are asked to prove such a thing, always the given set is non-empty. So you say let x, simple x belongs to capital X. But if you want say better to say be arbitrary, then you will prove Px. Suppose you want to disprove for every x belongs to, simple x belongs to capital X, Px. How do we disprove?
We have to show that there exists x in x such that Px is not true.
Not Px. Okay, very good. Proof of a universal statement. Proof of a statement with more than, I guess you guys can do this. Proof of induction. We have to do that. Yes. Because induction is a big thing for us. In his case, it was induction. Let's talk about induction within this 25 or 30 minutes. We should do one or two problems with induction because in our course, induction lesson was lousy. However, now you guys know the relevant logic, you know, no? Logic part. That's very good. There is, if you find time, read the remaining chapters. They are not that much useful to do mathematics, but I myself don't know places, whether there are places at which you are going to use it. So we are going to discuss, there are three types of inductions. One is forward induction. Three types of inductions. Three types. Of inductions. One is forward induction. Forward. You go from n to n plus 1. Forward induction has two methods. Second one is strong induction. It was mentioned in his book, strong induction. Normal one.
The normal things are
Normal. Because I am trying to finish as much as possible today itself, because next day I would like to do little things related to analysis. But these are very important. Normal induction. Other one is backward induction. Backward. So he begins from N0. No, I'm assuming you did A level. I won't act like as if you are still in A level. Let Pn be a statement state S-T-A-T-E-M-E about N. Suppose Roman 1, P1 is true. Let Pn be a statement about n belongs to. Is it thus? Suppose P1 is true, then for each n belongs to n, if Pn is true, then Pn plus 1 is true. Suppose this thing 1 and 2. Then Pn is true for each n belongs to n. This is the normal induction. This is the normal induction. If you in the place of 1, you can have 10 or any number, then for each n greater than or equal to 10. If you prove it here 10. So, if you want to apply the principle of mathematical induction for all of them, first you have to prove P1 is true, then you have to take any n belongs to n, arbitrary n, then you assume that Pn is true, no, conditional proof, then you prove that Pn plus 1 is true, it proves that Pn is true for all n. But can you see, there are at least 4 methods to prove second one. 4 methods, no? Because you take, there are 2 methods to prove first one. What are they? 2 methods to prove P1 is true. What are these 2 methods?
Direct proof and
Eh?
direct proof and
Direct proof and
contradiction.
very good. Direct proof and proof by contradiction. There are some misstatements. P1 you cannot prove direct. Then you have to go for proof by contradiction. Then second one, you take any n belongs to n. You want to prove this conditional statement. There are 3 methods. Assume this one is true, prove this one. Assume this one is false, prove that this is false. Assume that Pn is true and Pn plus 1 is false and get a
Contradiction.
contradiction. So over there are 3 methods. Other method is you assume the whole statement is false. Right? You assume the whole statement is false and get a contradiction. So there are 4 ways of doing it. In A level, actually, you don't have no induction problems. All you do is anyway, you take an arbitrary n, you prove it, assuming Pn is true, then you prove Pn plus 1 is true. That's the only method you do. But now you know that there's many induction problems, you cannot do that way. You have to, sometimes you have to assume this whole statement is true, false, and get the contradiction. Sometimes you prove conditional proof, prove by contradiction, prove by contradiction. 4 different methods of proving Pn is true for each n belongs. I wanted to have some problems, no? Yeah, there is time. Let's do 1 or 2 problems from here. Listen, I want to do an interesting problem. Forgot to do it. Other thing, I want to go to the restroom almost like this. Let me go and come. They are not in our course. They are, I don't talk about that kind of inductions because they are too advanced for us. Let us see. I wanted to have some problems, 3 or 4 problems. But let's say from this book I want to get the one backwards. We don't want to go backwards. Forward one, strong induction also. So I may have to do. Oh, I said I am going to complete induction today. I may not be able to finish it. So next day, 10-15 minutes to finish the induction. 59, so good problem. I want to show you certain things. Okay. Prove that every integer greater than or equal to every integer greater than or equal to 12 is a sum of two non-negative integers, sum of two non-negative integer multiples of multiples of 4 and 5. You understand the problem, no? I am trying to say, is that right and correct? Prove that every integer greater than or equal to 12 is the sum of two non-negative integer multiples of 4 and 5. But what it is saying is, if you take any number greater than or equal to 12, you can express that as 4 times some number plus 5 times some number. For instance, 12, can we do that way?
3 times 4.
3 times 4 plus 5 times
0.
0. 13,
5 times
5,
1.
2 plus 2 times 4 plus 5.
5 times 1. Like that. If you take any number, you can do so. So I am going to write then. Let proof. Let P in be the statement. There exist non-negative integers xn and yn such that n is equal to 4xn plus 5yn. Okay. We want to prove Bn. However, we are going to prove it for n greater than or equal to 12. So, let me observe that you said 12 is equal to 3 times 4 plus 0 times other is 4 times 3 plus 5 times 0. It's like x, no? Put the dot. My dot is bigger than a circle. 13 is equal to, you said 4 times 2 plus 5 times 1, 13. 14 is equal to 4 times 1 plus 5 times 2. No, these are true. Now I have proved the result for 12, 13, 14. But if I am going to continue this way, you have to wait till next year, see it. Okay, you have proved that. This is true because 3, 0, 2, 1, 1, 2 are integers, non-negative integers. So I am not writing all that. Now I have to prove it for now. It will be shown. Now, okay, let's find this way. Let us use induction. Let us use induction to prove what each n belongs to n. such that n greater than or equal to 15. Pn is true. I have proved separately Pn for 12, 13, 14. Now I am saying for the rest of the integers, I am going to use induction. N greater than or equal to 15. Right? You can see 15 is equal to 4 times 0 plus 5 times 3. 0, 3 are non-negative integers. So my, according to this one, now it is not P1, P15. Now here, for each n belongs to n, such that n greater than or equal to 15. I want to prove if Pn is true, then Pn plus 1 is true. 15 thus P15 is true. P15 is true. Now I have to say, what do I have to say now? Suppose that
for each n belongs to n.
no. When you are writing the proof, for each n belongs to n doesn't come.
Suppose that Pn is true.
Suppose that?
Pn is true.
No, I don't know anything about n. No. What should I write?
That n belongs to capital N such that Pn is true.
Suppose that n is an integer such that n greater than or equal to 15 and Pn is true. Whether you write this statement or not, whatever you write must include this thing. N must be an integer greater than or equal to 15 and Pn is true. Right? Now I want to prove that Pn plus 1 is true. Pn is true. Thus, there exists x and y n non-negative integers such that n is equal to 4xn plus 5yn. Right? I have shown here for IU. Good. I am writing, I don't write everything. Here I should have written, therefore P12, P13, P15 are true. Right? Let me write it anyway. Therefore P12, P13, P14 are true. Now let us use induction to prove that for each Okay, now I took an integer n greater than or equal to 15 and Pn is true. Therefore, there are non-negative integers xn and yn like this. Thus, n plus 1 is 4xn plus 5yn plus 1. Right? Now, however, I want to write this thing as 4 times alpha n plus 5 times some beta n. I have to do that. As you let me not be able to finish it today. As xn is non-negative, xn greater than 0 or xn equal to 0. Right? It is non-negative. So case 1. Assume xn is strictly greater than 0. Oh, the pins are not right. This pen will write. Let's see. Only you could see. Hence, xn minus 1 greater than or equal to 0. Thus, n plus 1 is equal to 4 times xn minus 1 plus 5yn plus 5, because 4xn plus 5yn, here minus 4 plus 5 is plus 1. Therefore, this is equal to 4 times xn minus 1 plus 5 times yn plus 1. It is clear that xn minus 1 greater than or equal to 0. I have written upstairs, and yn plus 1 also greater than or equal to 0, and xn minus 1, yn plus 1 are integers. Therefore, in case 1, Pn plus 1 is true. Do I have a case 1? Case 1 is. So I have proved the result for case 1. Case 2. Now, assume xn equal to 0. Hence, because n is equal to 4, my xn is 0 now, 4 times 0 plus 5 times yn, because of this thing, greater than or equal to 15, my n is greater than or equal to 15 now. It follows that yn greater than or equal to 15, yn greater than or equal to 3. Right? Thus, yn minus 3 greater than or equal to 0. So, n plus 1 equals 5 times yn minus 3, yn greater than or equal to 3, therefore this one greater than or equal to 0 plus 5, 15 plus 1, because my n is 5in, so 5in here, minus 15 plus 15, cancel out, plus 1 here. This is equal to 5 times yn minus 3 plus 4 times 4. Clearly, yn minus 3, 4 are non-negative integers. So I have written in case 1 when xn greater than minus 1 when xn greater than or equal to 0, I proved the result is true. Now if xn is equal to 0 again, I have proved the result is true because yn minus 3 is non-negative, 4 is also non-negative, and they are integers. Thus, in case 2, Pn plus 1 is true. Hence, in either case, in both cases, Pn plus 1 is true. Therefore, by the principle of mathematics, induction, induction, mathematical induction, for each n greater than or equal to these pins. Now let's go to this one. Induction for each n greater than or equal to 15. Pn is true. Right? We already know that. Can you see the reason I am doing this proof? I will let you look at this. We already know that P 12, 13, 14 are true. Hence, for each n greater than or equal to 12, Pn is true. If n our like value and another, hence for each n greater than or equal to 12, hence for each n greater than or equal to 12, there exist non-negative integers. There exist non-negative integers x and y n such that n is equal to 4xn plus 5yn. So I have wrote the reason I selected this problem. Though I solved it by induction, can you see? Here I have written. Therefore, by the principle of mathematical induction for each n greater than or equal to 15. So here I did not write hence for each n greater than or equal to x. There it is non-negative integers x and y in such that though I use induction to solve this problem for 12, 13, 14, I solved it independently. After 15 only I have used induction. So you need to be very careful. Many problems are like that. You are not going, if you started from 12, you cannot prove it. If you started from 13, again you cannot proceed. If you started from 14, again you cannot proceed. And if you start from 15, I proceeded. So you need to be careful. If somebody says, I solved it using induction, doesn't imply that he proved the result using induction for every integer for which he is claiming. Some of the integers may be independent proofs, some, of course, induction. Need to be very careful. So let's do one or two problems next day, and I will say a few words about one problem from by strong induction, because nobody is going to teach you them. Then I will say give the definition of backward induction, then go to epsilon, etc. Abogolian. But this is very important for you to know because you may not have seen such an example before, because you know in A level you don't have very good induction problems. You need to be very curious when somebody says he solved the problem using induction. You have to wonder whether he has used induction for all the integers. For some of them, like here, may be independent solutions. So I will do one or two examples from induction next day. I will go to strong induction, may solve one problem, so that you can, you are an intelligent guy, you can do the rest. And I will not use backward induction. I don't know, nobody is going to teach you. As a result, I will do that also. As a result. Okay. Did you learn something today?
Yeah.
Yes.
Yes, good.
Stop.